Okay. Welcome. Today is going to be PA2 session PA2, which is predictive analytics 2 and supervised algorithm. Okay, and I want to tell you what is meant by unsupervised algorithm first, and then we go after other things. Unsupervised algorithm is there is no supervision of the outcome. That's all it is. No supervision of the outcome. In the case of supervised algorithm, we have a supervision of the outcome. Okay, sometimes it may look like I'm looking up, right? Do I see like I'm looking up now? That's because I'm looking at a big screen. And it is easy for me to see the big screen because I can see this is a UHD 40-inch screen for me. Like your 40-inch, I have a 40-inch here, but very close. Okay, and when I see a 40-inch, I can see all of your face, Are you upset? I can see all those clarity. But I'm looking at the laptop here. Now I'm looking at laptop, which is what I look at when I explain things. Okay, so don't get kind of disconcerted. Hopefully not, right? Ilana, I have to shut down my big screen. Just look at this one. Okay, I can do that. Now, I talked about what is meant by supervised algorithm, unsupervised. Everybody clear? Very clear, right? So can you think of a situation where there is no outcome, but we have data? Not that you already should have known that, but I'm saying there is no outcome. There is no outcome. Can somebody tell me? You always have to interact with me. You are committed to that, right, everybody?
Yes, sir.
In the group, yes. Ready to interact, engage, talk, converse, ask questions, challenge. Everything is cool. Thank you. So, think of an example where there is no outcome. What does that outcome mean to you? First, let's understand what is meant by outcome. We are concentrating on an outcome. Go back to examples we saw. You can extract the definition.
Stable, true, false. The outcome.
Not able. What did you say? Not
class label.
Class label, but that label can be on the right side also of a model. Right? For example, if it is a high income, low income model we create, right side could be educated, not educated. That's a class variable, right side. Okay, so will you call that as a situation of unsupervised? One more try, and then I'll just say, okay, one more try. Somebody?
The answer is either 1 or 0.
What is that?
Supervised algorithm is where the answer is either 1 or 0. We have an output of 1 or
0. Okay, is that Shivats?
Yes, sir. Either 1 or 0. That's
okay,
an outcome.
Answer. Okay, the keyword I see is answer is 0 or 1 or 1 as well. Right? But by answer, he means you didn't explain it that way. I'm going to say you mean that is you are able to explain an answer 0 or 1. Right? Explain an answer. That's what supervised means. Explain an answer 0 or 1. But it doesn't have to be 0 or 1. It can be continuous variable also, like income.
Yeah, I'm just giving an example here.
You are explaining the income, which is a continuous variable, not a 0 or 1. In other words, there is a dependent variable. Okay. In other words, you are explaining something. That's what supervised algorithm is. Okay. Everybody gets it? If you are either explaining something or you say this is a dependent variable, dependent on all the other things to explain. Can you give me an example of one supervised algorithm you did in the class? Other than income, we did income, right? Other than income. Go. நிறைய பண்ணோம் இவரெல்லாம் பண்ணாரு ஜேகே எல்லாம் பண்ணாரு ஞாபகம் இருக்கா Shalom, what is it? What example? Just jump in.
House pricing. House pricing.
Yes, that's a surprise. Everybody agrees now? You are explaining house price using lots of variable. That's good. Another one? Other than has been telling. Okay, anybody else?
Diamond data set based on the carat size and all.
Diamond data set, what were we explaining there?
We were explaining the price based on carat and the size, that is X, Y, Z at depth.
Right. So diamond data analysis, where you are explaining the price is a supervised algorithm. You are the explanation of the price is supervised. That's what it means, really. Okay. These are all computer science people's terminologies, and then data mining people terminologies, and the new world data science people terminology. Statistician used to say, it's a dependent variable. That is a dependent variable. Same thing. So in the case of unsupervised algorithm, we don't have a dependent variable. That is the point. Get it? We don't have a dependent variable. So what does that mean? Think of a situation where we don't have a dependent variable. Can somebody think of that situation? Yeah. I'm coming. Can you think of a situation where there is no dependent variable? Can you think of a situation where there is no dependent variable?
Anything dependent on time will also be a supervisory variable, right?
Yes.
Time on x-axis, will it be a dependent or supervisory or unsupervisory? Because it's a kind of dicey situation, so sort of.
Yes, it is. You're right. Sorry. Yes, you're right. Time is also. In fact, time could be. Remember, there are complex time-based models also. Called, for example, complex dependent variable, where the dependent complex dependent variable, which involves time variable also. Okay, but there are methods called simultaneous equation models. Time series models with with the dependent variable, or ARIMA X models, and so on. Okay, so but the main point is I'm talking a situation where you have no dependent variable. That means you have data. Can you think about a situation where you have data and you are explaining something? What does that mean? What could it mean? Think about it. A few things. If you haven't heard anything, that's fine. If you can think of it, that's fine. Any situation? Okay.
Will it come under stock price? Will it come under unsupervised? Anyway, it just happens. That's all. Just bid and selling without considering any.
No, you are explaining the price.
Okay.
You are specifically explaining a price.
Okay.
Price movements, right? So how about this? We want to know that there is a whole collection of data, and we want to know whether we can reduce the number of variables, collection of data, to a smaller dimensions.
Okay.
No dependent variable here. We are just saying we are analyzing to reduce the dimension of the data, which is very common in big data. We are reducing the dimension of the data. No dependent variable there. You might say, I'm looking at that screen. I don't want to look at this. Oh, I'm going to pull out this. Can you hear me? Okay. It's come. Give me a minute, it will come. Sometimes it's, it happens, something happens, so I'll have to fix it. You are not able to hear me?
Yes, sir.
Okay, it came back, right. Cool. So, okay. Let me, boy. All right, it's better now. So, You might say, well, I'm explaining the dimensions. You might say that, right? No, that is not what we are talking. We are talking, we are not talking about, supervising the dimension here. Supervising some explanatory variable is what is called supervised model, but not, reducing the dimensions. It may look like, well, I'm also explaining the dimensions, whether it is 5 dimensions or 10 dimensions and so on. But it is an explanation, but not specific to a, outcome variable or action variable. Okay, everybody gets it? So far so good. So dimensionality reduction is the huge collection of dimensional reduction methods is unsupervised algorithm. How about clustering? I got data. Let's say birds, feather size, color, the beak, length of the leg, how many talons are there, how long the tail is, what is the size of the whole bird, all these things if I have, and probably let's say 100 variables. Is it possible to categorize, group the birds? Can I do that? I can do that. It's, because our vision is actually collecting all this information and processing it in your brain. So it is a, we don't know, we are not talking about specific outcome variable here other than, finding groups in the data. It's a blob of data that we either reduce the dimensions of the groups, find out the groups. These are all examples of unsupervised algorithm. One more thing. You see Netflix movie recommendation. You all have Netflix. How many of you have Netflix?
Yes. Here.
Okay, most of you have Netflix. What do you need in the class? IOA, what's going on?
We had some disturbance, so now it's rectified.
Now it's okay. All right. Yeah. So recommendation engine. Netflix is one great example. There is no specific outcome we are talking about. Okay. There is no specific outcome we are talking about, but based on your, experience in the past, I want to recommend what would be better for you. What would you like to watch? Because oftentimes it's important, because when you have 100,000 products or 100,000 movies, 100,000 products or 100,000 movies, it is better that the நம்ம ஊர்ல செட்டியாருங்கெல்லாம் ஒரு கடைக்கு போனா அப்பெல்லாம் செட்டியார் தான் கடை வச்சிருப்பாங்கன்னு அர்த்தம். நான் ஒரு பழையங்காலத்து ஆளுன்றனால சொல்றேன். இதுல ஒன்றும் it's not racial or anything issues, but I'm just explaining. It's fun, It really happens even in a gramam in Tamil Nadu. Recommendation engine. There is a recommendation engine going on there. The store owners know இது ஏதாவது இருக்கா கேட்டீங்கன்னா அவங்க என்ன சொல்லுவாங்க, இது இல்ல சார் அது இருக்குன்னு. They know that you are looking for a similar item, right? They know. When you ask question, they know what you are looking for. They will recommend a similar item that matters to you. That's a recommendation, right? And can we automate that? That's what recommendation engine is. Okay, there is no outcome variable here. Broadly speaking, there is no outcome variable here, but given a data, we want to provide some recommendations. Okay, that's another thing. Cluster analysis, recommendation engine, as well as dimensionality reduction, all these things belong to not unsupervised algorithm. So that's what we are going to learn going forward. I was telling you what is meant by unsupervised algorithm. But now I have mentioned the answer. They all were waiting, thinking, all those things you passed. Okay. You got the answer. Okay. So please, talk to others, if clarify what it means and so on. But the examples are cluster analysis, dimensional reduction, huge collection dimensional reduction. Broadly speaking, principal component analysis, and then factor analysis. These two are, broadly speaking, dimensional reduction methods. Okay, and also one more method called correspondence analysis. Those are the three different unsupervised algorithm that are used in dimensionality reduction. Interview what is meant by dimensional reduction? Can somebody tell me? What is meant by dimensional reduction? Reducing the huge number of dimensions in the data to a meaningful small number of dimensions, meaningful interpretable small number of dimensions. Okay, put it as interpretable. Okay, is called dimensional reduction method. And cluster, yeah. Go ahead, Arun. You want to say?
Break ఇక్కడ కొంచెం కష్టమైంది.
Oh, nice. So cluster analysis, I'll try to speak slowly. Hopefully it will work. Cluster analysis, it's also a dimensionality reduction if you look at it, you will think about it. Okay, what are we doing? If you think each record is one on the row side, see, on the row side, if you think each is one dimension, like each individual is a dimension, right? Then how do you group them so that you have fewer segments, groups? Okay, so you are reducing the dimension. So clustering is on the row side. What is row and what is columns? Can somebody tell me? I always use this, row versus column. What is row and what is column?
Column is the different variables in the same data set.
Right.
Row, like all the variables for one row. Like
observation. Row is observation. Yeah. Row is an observation. Columns are variables. Always remember that. Abhi, concentrate here. Very important distinction. What is row and what is column? Always rows are observations, columns are fantastic. Always remember this. Data is always structured like this. Rows are observations, columns are variables. They are called observations or experimental units. Okay, observations. Always remember this. This is how a data set comes to you always. It's a rectangular format. Always, unless it is a unstructured data.
Like image, video,
or audio, all those things are unstructured data. They have a different structure, but the point is most of the data, people say that unstructured data is 95%, structured data is 5%, but we have been solving only 5% of the problem. That's what they are saying so far. Okay, but the point is, you have to understand the unstructured data analysis very well. Structured data analysis very well so that you can understand the unstructured, because it's complicated, right? So always because of the traditional data have been coming to us always in a rectangular form. Rows are observations, columns are variables. So I'm coming back to, if you reduce the dimensions of the rows, it is called cluster analysis. If you reduce the dimensions on the columns, or traditional dimensional reduction problem like principal component analysis, factor analysis, correspondence analysis. Okay. Okay. Now you may still have a question. Sir, okay, fine. What do I get out of it? Right? You may have that question. Anybody has that question? I explained, but you still may have that question. Okay, what do I get? Why do I have to spend my time here on these things? Anybody has a question still? Sir, that is a fundamental question. Huh?
Reduce dimensions of columns or the
reduce dimension பண்றதுனால என்ன benefit? So I have 100 dimension data, 1000 dimensions. In big data, a lot of dimensions, a lot more dimensions. I reduced it to 4 dimensions, let's say, or 3 dimensions, I would say. What is the benefit of that?
Easy interpretation.
Easy interpretation, exactly. But you might lose something, isn't it? You might lose because there is nothing free. Okay, you are reducing it, you lose something, but you want to make sure you don't lose too much. You know, this is the statistical world, right? Okay, you kind of, work with, the difficulty is, but at the same time, don't lose too much, difficulties and get the maximum, most out of it. Agreed? So we will always continue to do that. Even in regular analysis, whatever you did, regression analysis, whatever it is, classification analysis, we did capture the maximum information in the model through the model, maximum information in the data through the modeling. Okay, so that is our purpose always. We want to simplify, we want to model, but through the process, you are going to lose something, but make sure you don't lose too much. Okay, so under dimensional, the two moon dimensional, the null. Your boss will be happy, right? Okay, you'll be in control of the communication, right? Okay, so how do we do it? That's what we are going to solve. Is that a reason clear to you why it matters? So that is on the, I said principal component analysis, factor analysis, or on, correspondence analysis, or on the column side, variable side. What is factor analysis? Factor analysis. Principal component analysis. Principal means main. The meaning is main, important, right? Principal. Who is the principal of the school? He is the main person, principal, right? Main person. Principal dimensions. We want to find out the principal dimension, principal components. Components means dimension. Principal components analysis. Factor analysis. Okay. There is something deeper here. It is not only reducing the dimensions. Listen very carefully. What is factor? I'm going to talk about all those things, explain to you all those things. Right now, I'm kind of introducing you. Logically, I'm trying to introduce you. So it's not only reducing the dimension, but also finding the dimension in a hidden space. The main space is hidden space. Right? But that's the beauty of mathematicians, statisticians. On the hidden space, mathematically we will bring it out. That is what factor analysis. So it is what is also called the latent factor analysis or latent analysis. Latent analysis, factor analysis is always latent. Okay, it's a latent dimensions. You can call it as principal latent dimension, principal latent factor, principal component analysis. You can say principal latent component analysis. That is what factor analysis is. I think that is a better word. But people don't use, they don't use just better word. They just want to use some word. It's a problem, but don't worry about it. We can say it. You can say in my class, I'm fine. When you talk to your manager, you can tell them. They might get confused. They will be confused even about factor analysis. Okay, but really the spirit of that analysis is that it is a principal latent component analysis, which is also same as principal latent dimension reduction method. Am I right? Yes. Because I used principal components analysis, principal dimension reduction method. Let's see what I mean. First, we will go through principal component analysis. Okay, now let's go through this. Are you there, Srivats? Are you there?
Yes.
Okay, thank you. All right. Okay, I'm going to close. You might still see me, but I'm going to close here so that I can start talking here. Okay. Yeah.
So just to summarize, because the terms, whatever you were saying, like sometimes we were not able to hear completely. Just whatever I've understood, I'm just saying just to summarize and confirm our understanding.
Yeah.
Like we discussed rows are observations and columns are variables, and as part of unsupervised algorithm, we are focused on reducing the dimensions of the data. When it comes to reducing the dimensions of rows, we do cluster analysis. When it comes to columns,
I don't want to say use, but that is what termed. It is termed.
okay.
Okay, go.
Reducing dimensions of rows is termed as cluster analysis.
Yes.
Okay. Reducing dimensions of columns, we have different methods like principal component analysis, factor analysis. They are different methods, are they?
To reduce the dimensions on that side, column side, variable side. Remember, each variable. Okay, go ahead.
Are they different methods like whatever we discussed? Principal component analysis is one method, factor analysis is another method.
Yes, and also correspondence analysis, third method. Okay, what else? So the differences happen. I explained what is the difference between principal component analysis and factor analysis. I explained that to you, right? Principal component analysis is dimension reduction in the originals variables, in the given observed variables. Factor analysis is dimension reduction in the hidden variables. Question எங்க சார் hidden work போகுது அதான் explicit வந்துட்டு observed variables வந்துருது எங்க hidden variable இருக்கு, right? Think about this situation. Measuring intelligence, right? Measuring intelligence.
Factor analysis means dimension reduction in hidden space.
The hidden space, yes.
Finding common hidden spaces. Same.
The method is factor analysis, also called latent factor analysis. You can say sometimes people say latent analysis. I say all these things. It is really principal latent component analysis because you are really reducing the dimension in the hidden observation space, but which we don't observe. We observe, and I'm giving you an example. Our interest is to observe intelligence. Intelligence define பண்ண முடியுமா? We think we define. இதை போடு அதை போடு கட்டமா போட்டு டாட்லாம் போட்டு நம்பர்லாம் போட்டு we think we measure intelligence. But intelligence is our interest, our dimension of interest. But we give all kinds of other measurements. We take all kinds of other measurements. Each one of them is a variable in the observable space. But we are using that to measure the hidden space. Agreed? Make sense? Enappa, Satya? Rumbo important. Even for everywhere it's important. Not only in behavior science, it's important everywhere. How do we find the hidden variables? Because observations are whatever we observe, they have errors in observation, right? Because intelligence, various tests put together, you will see some examples. There may be some 20 tests you will use to figure out your math intelligence, your articulation intelligence, your comprehension intelligence, all those things you may try to explain. So you have 20 dimension space of observation. You are trying to find out the most important 3 dimensions in the hidden intelligence space. Space means it's an observation. Don't worry about anything. It's not, we are not talking about, space flying out of this universe. galaxies and all. I'm not talking about that. I'm talking about the observational space. Because we can contain it into a 3-dimensional space is clear in an observation, right? 2-dimensional space is clear, like that multi-dimensional. Now we are mathematically thinking. Point is, no, we can. Is there a possibility that we can reduce the observation of 20 plus or I don't know how many number of tests people conduct, so many number of tests they conduct, but eventually they want to find out those 3 things commonly, right? Your dimensional view, understanding, your ability to move in the 3-dimension. These are all issues. When you have some difficulties, in our mental processing, people have difficulties in interacting with the real world, right? So all these things are measurable in the hidden space, which we want to measure, but we cannot do that directly. We measure using the observation there. Okay, so it's actually measuring that hidden space with some errors. The point is, can we get to that lower dimensional space of the hidden space? That's what the factor analysis is. Everybody clear to me? Clear with you? Is this? So if somebody asks you what is factor analysis, will you explain? Can you try somebody? This is an interview question because it's really complicated. இன்னும் நீங்க போடல எக்ஸாம்பிள்லாம் போட்டா இன்னும் நல்லா தெரியும். You'll be able to explain. But I'm just telling you, people ask this question commonly. What's a factor analysis? What is the difference between principal component analysis and factor analysis? They'll ask you this question. And you are the master, I tell you. When you go there, you are the master. You know how to say it. Correct? What is the difference between principal component analysis versus factor analysis? Okay. Fine. After you see some example, you will say. Okay. Let's go through that. But fundamental to all these things is matrices. We are all committed to matrices. Okay. Fundamental to all these things is matrices. So really, matrix transformation is what is going to be used here to do all our work, all our tricks, all our mathematics. Okay. So, all right. So what does that mean? Okay. Let's go. So I introduced you this. You remember this equation? You remember? You're to talk. If you because I'm not seeing you from now on. Okay, only your loud voice I can hear. This I introduced. Yes.
Yes.
Okay. So here I introduced because I want to introduce matrices, and matrices are transformations. They transform this values into these values. Are you with me? Can I say that way? So far, I didn't say that word matrices are transformations. I'm saying it now. Matrices are transformations that transform a vector into another vector. And everybody gets it?
Yes, sir.
Excellent. And write down that sentence. Matrices are transformation. Look at this one. Actually, using a right matrices, this is Tx, okay? This is a dimension Tx. This is dimension Ty, and this is a M, right? This is a M written here. All these points are all points in a 2-dimensional space. Everybody agrees?
Yes.
Yes, sir.
And the 2-dimensional M, இவ்வளோன்னு இருக்க சும்மா இருக்க M பூதம் போல இந்த மாதிரி போட்டு காண்கலாம் கம்ப்யூட்டர்ல டக்குன்னு மாறிடும் using a matrix transformation. That is what is happening in your graphics, in your games. That's what is happening. Do you believe it? Now maybe. Yes.
Yes.
So உங்களுக்கு வந்து இதுல வந்து if in the matrix and the games, computer games, it's all about really matrix transformations. Okay, suddenly ஒரு பெருசா காமிக்கணும்னா ஒரு மேட்ரிக்ஸ் ட்ரான்ஸ்ஃபர் அதான் இது வந்து டிரா பண்றது கிடையாது. That's what I'm trying to say. Do you agree with me? They are not drawing, they are transforming using a matrix. Okay, இங்க பாருங்க ரொட்டேட் பண்றாங்க. இந்த M இருந்த M I rotate like this, right? The original M. That is also transformation, matrix transformation. This one is skewed. The last one is skewed. Are you with me? சொல்லுங்க உங்க பேர் டக்குன்னு வர மாட்டேங்குது. You first row.
Me, sir.
Yeah.
Prashant.
Prashant. Sorry about that. I don't know. Okay, sorry. But I want to face that difficulty with you. Just I'm not able to remember. Please remind me. I hope you don't mind. So this one is skewed, this one is rotated, this one is expanded, scaled. All these things are just matrix transformation. Okay, in other words, you are multiplying all those points with this from some specific matrix. That's what it means. You buy into it. Okay, I kind of went into transformations, definition, and then why it makes sense, that definition, cool in definition and so on. But we are going to go, our purpose is really to reduce the dimensions. Okay. Okay, now let's keep going. I have some good references. If you're interested, you should go and read all these things, okay? Computer drawing is matrix transformation of points, very important. Explaining the matrix transformations, more visuals are here, okay? I'll just go there and come out. See, Araga, F is the one, right? F is now shifted, translated, it's called translation. Your 3D games are just work of art using matrices. If you just multiply all these points, the F points, by this one, nothing will happen. That is called identity matrix or no change matrix. Are you with me?
Yes,
Everybody? If you multiply all these points by this one, pre-multiply, nothing will happen. That's why it's identity or no change matrix. If you want to move, translate, okay, translate, then you have to use this matrix. Okay, are you with me? These are all just, this is just after a lot of research, people figure this out. So don't worry if you don't know, they do a lot of research. So don't get upset about that. Are you with me?
Yes.
At this time, you are learning from others. This is scale about the origin. Okay, shift okay, that is because you are pre-multiplying by this matrix. If you want to rotate, you have to multiply by cosine theta, sine theta, minus sine theta, cosine theta. Okay, if you are rotating, rotate about the origin. Depending upon the angle, all these points will move. Are you with me?
Yes.
In the same way, shear. This is shear means, you are kind of moving only in one axis. You're keeping the other points on the constant, but you are moving this one, this axis. Are you with me? So it's not anymore 90 degrees angle between x and y, but something different. That is called shear. And for that, if you want to shear this, you see how F has changed from here. This is a lighter color F. That's the original. This is the changed color. This kind of shearing is can be achieved by this transformation. Now, what about reflect about y-axis? You use this one. You use this matrix, then this will shift like this. In no moment. You just have to multiply all the points here. Are you with me?
Yes.
Everybody? Because I'm not seeing you. You have to say yes or no. Reflect about the origin. So in the diagonal in the matrix use pannu. Reflect about the x-axis na idu choose pannu. Is everybody finding it interesting, fun so far? Just the importance of matrix transformations. Everybody's with me?
yes, sir.
Okay, good.
Yes.
So, matrices of transformation, they transform the matrix times the vector, transform the vector into a new space. That's all I'm saying. Write down this one. Matrix times the original vector of points moves the transforms the points into a new space. Right? New space. Again, space na in that வேற வழியில அந்த வேர்ட் யூஸ் பண்ணிருக்காங்க. It's கொஞ்சம் ஒரு மாதிரியான அட்வான்ஸ் வேர்ட் போல தோணும். அதெல்லாம் ஒண்ணும் கிடையாது. It's a multivariate observational space அப்படி வெச்சுங்க. Now,
Sir. into vector points is moves the
No, matrix times the original points maps it into the new space. That's all I say. Maps it into a new space. Right? இங்க வந்து இதெல்லாம் வந்து new space தான். இது பாருங்க இதெல்லாம் வந்து new space தான். But it is represented in the same axis. அதனால தான் வேற ஒண்ணும் இல்ல. புரியுதா? இப்போ இங்க all these examples are new space now. It is moved into a new space of observations. You know, I will show you one more example. Then you will know. Okay, it's very far, very far. Okay, look at this one. So here is a claim I'm going to make. There is a matrix. If I use that pre-multiply this vector by that matrix, it will move this, you know, it will map this point to this point. Do you agree? If I mean, there is a matrix, you know, pre-multiply this observation with that matrix, that will move this point to this point. In fact, it will move all the, you know, can you find that matrix that will move all the three-dimensional points to this two-dimensional space? Are you with me? With that statement.
Right. The third dimension will vanish and all of it will get mapped to only one point.
No, not all of it. Right now, I'm only saying this point is mapped to this one, and you know, I haven't extended the thought beyond that right now. Okay, I will come to that.
Okay.
Okay, he asked a good question. Everybody understands this question, and everybody understands my answer. Everybody understands this question. Okay, don't worry about the question. Do you understand what I'm saying? What I'm saying is, so far we understood that by keeping a matrix, pre-multiplying a matrix, I am mapping the XYZ point into a new three-dimensional space. Let's say three-dimensional space. Okay, it may not be the same point. That is not interesting. That is the identity matrix. That's not interesting. But I'm saying, if you have understood that, and we saw that all kinds of application, like in the graphics, you know, how it is happening, translation is happening, upside down, this and that, and so on. Okay, now you park those ideas, and then I'm saying, so can I find a matrix which maps this 1111 into this 202? There must be a matrix, that you agree. Okay, that's good. That's good. Everybody agrees there is a matrix. Can you try to find that one? Can somebody tell me? Try to think. And try to find what could be that matrix. If I multiply that 1111, it will come out to be outcome to be this one. The output, not outcome. Output to be 202. Just think about it. Try.
Diagonally 02, the rest are zeros. Diagonally 202 and the rest are zeros.
You get it. You get it, correct. Everybody understands. It's a diagonal matrix, and the diagonals on the 202, matadala 0, and the matrix sending a 111. Everybody agrees that.
Yes, sir.
Actually, you should check it out. I mean, it's okay if you get it mentally, you get it, that's fine, but you should check it out. Because I'm going to ask the next question. And somebody else should say the answer for that one. I want that to be 101. No, 101. I want that to be 123. It should map 111. Should be mapped to 123. So, can you give me an example of a matrix that will, if you use it to pre-multiply, it will output to 123. Are you with me, everybody? Is the question clear to you? The question is, what is the matrix? If you pre-multiply this 111, the output will be 123, not 202. Okay, you are saying diagonal is 1, 2, 3. Okay, that's a clever. I don't want such a diagonal matrix. Is there anything else? Can you give me another example? ரொம்ப simple example தான். Try. என்னப்பா சத்யா, how is it going? Are you with me?
Yes, sir, but கொஞ்சம் delay ஆகுது understanding.
No problem. But you understood the main point that there is a matrix that can be used to transform from one type of dimensional data to another type of dimensional data. That you agree, right? Okay, good. That's okay. But I want to ask this question: what is the other than the diagonal matrix 1, 2, 3? Give me another example. No, is it possible or not? I think it is possible. So, anybody?
Only diagonal 1, 2, 3. The previous answer was diagonal to be 1, 2, 3, right? This time we can use identity matrix into 1, 2, 3. That is column 1, 2, 3.
I want to remember this. I'm talking about this specific example. This example, anga point 1, 1, 1. It should be mapped into 1, 2, 3. But I don't want a diagonal matrix.
Identity matrix used for it, and you multiply with a single column. The column consists.
Multiply பண்ணி காமிங்க பார்க்கலாம்.
100.
என்ன பாலா?
1, 2, 3 ஃபைனலா வரும்போது ஒரே காலம்ல வேணுமா சார்? இல்லனா 1 வந்து C11 ல இருக்கணும், 2 வந்து C22 ல இருக்கணும், 3 வந்து C33 ல இருக்கணும், அந்த மாதிரி வேணுமா? இல்லனா
that is a diagonal matrix. That is your the transformation matrix is diagonal. I don't want that. I want other than diagonal. I want to be careful in using the words. I want other than that specific example you gave 1, 2, 3. Is it possible?
1, 2, 3 minus 3.
என்னப்பா என்னது சொல்லுங்க.
First column 3 அப்புறம் minus 2 minus 3 அப்புறம் 1, 2, 3 இத வந்து அதோட மல்டிப்ளை பண்ணா 1, 2, 3 ன்னு வரும்ல.
இல்ல சொல்லுங்க, எனக்கு கேட்கல சரியா. Tell me that the first row. Many ways to get it. I want you to get impressed that there are many ways to get it. Many matrices are there and they all have a relationship. I want to come there. Go.
First column 1, 2, 3. Second column -1, -2, -3. Third column 1, 2, 3. In the matrix in the 1, 1, 1 ஓட multiply பண்ணா நமக்கு 1, 2, 3 வந்துரும்.
Okay, first one is 1. Good job. Okay. 2, 3. Good job. Okay. Good. That's fine. Is there only, you think, if the problem is solved, there is only one more? Is there another possibilities are there?
Yes.
Okay. Why do you think there are other possibilities are there?
Why do I think?
You gave me an answer. Well, there were 2 answers were given, right?
Yeah.
I wanted to understand. It's a good progress that we are making. My point is now, and I mentioned also that there are other. I asked you and you agreed that there are other possible ways of constructing this matrices as transforming entities. Okay, matrices are transforming entities that transforms one point to another point. There are many ways to do that. There are many matrices available, but they all have some relationship. Okay, they all have some relationship. So if you put one, if I will come to that word, they all have some relationship. I will come to that. In this example, what you are saying, 1, 1, 1 is transformed to 2, 0, 2. In this example, one is to transform 202, and one of the ways to do that is to use the idea 200 tool. Yeah, so 200, which he said, right? 200 000 002. And interestingly, it suppressed one of the dimension. Watch out very carefully, everybody. It suppressed the middle dimension.
Correct.
It nullified. It ate away. Right? It nullified. It ate away the middle dimension. It can be any other dimension, but in this case, it's a middle dimension. So, in other words, that kind of matrices. It could be, A000 00000B. Let's say the whole thing. If the transforming matrix A00 00000B, where A and B are 2, is what came out to be like this. That matrix will always suppress because the rank is 2, not 3. Because this rank is 2. You know why rank is 2? The one of the rows is 0. All of them are 0. நீங்க படிச்சிருக்கீங்களா சத்யா? நீங்க மேட்ரிக்ஸ் எல்லாம் படிச்சிருக்கீங்களா?
படிச்சிருக்கேன், but ரிமைண்ட் பண்ண முடியல.
No problem. We'll kind of remind ourselves through our class. But இது வந்து லாஜிக்கலா தான் நான் பேசிட்டு இருக்கேன் right now. I'm not saying just giving you properties. I'm just asking you to think, leading you to these kinds of conclusions. Because இந்த ரெண்டாவது மேட்ரிக்ஸ் நீ அவர் முதல் ஆன்சர் சொன்னீங்கல்ல, அந்த முதல் ஆன்சர் 202 சொல்றேன். I'm talking about this one. 202, and he answered that saying that 200 000 சொன்னார் இல்லையா? That has only rank 2. Everybody agrees, right? Rank 2 means what? How many independent rows or how many independent columns are there? Let's all call it as how many independent columns. How many independent columns? Okay. That means you cannot, 2 of them you cannot write as a linear combination of others. That's what independence means. Two columns are there which cannot be rewritten as a linear combination of any other things. One cannot be rewritten as a linear combination of others. Correct? So that happens. 2 of them are happening, so it's called rank 2. That's what rank 2 means. And you can find that rank 2 in many ways. How many rank into them we can find out in many ways. I'm going to leave it to you because you read all those things. I'm kind of a little bit capturing from your experience, from previous learnings. So the question then looks like, and these are called linear transformations. See, it's a linear equations. You remember this is also connected to linear equations. So they are called linear transformations. Remember that. Matrices are representative of linear transformations. Write that sentence. Matrices are representative of linear transformation. So far, so good. Please, Srivats.
Good, sir. Good.
Okay. Are you an engineer, Srivats?
No, sir. Why?
Look at engineers. No. Are you a management person?
I'm coming from BCom, commerce background.
Commerce graduate. Okay. But உங்களுக்கும் matrix எல்லாம் படிச்சிருக்கீங்களா?
Yes, sir. In class 12 we studied mathematics.
Like Satya, I think, right? Satya, you did in class 12 maybe? Okay. Just we are trying to understand terminologies here. But at the same time, we want to think dimensionally. ஒரு ஸ்பேஸ் ஆஃப் அப்சர்வேஷன்ல இருந்து இன்னொரு ஸ்பேஸ் ஆஃப் அப்சர்வேஷன்ல எப்படி நம்ம வந்து கனெக்ட் பண்ண பாக்குறோம்ன்றதான் இப்போ பேசிட்டு இருக்கோம். ஏன் அதை பேசுறோம்னா, when you reduce the dimension, you have to find the right matrices that will transform the original dimension into lower dimensions. Okay, and by the graphics examples I showed, that matrices are also transforming or rotating the space. You saw that example, right? I gave examples, graphics example. It rotates, it can reduce the dimensions, it can rotate the space. In other words, the whole original space you have to rotate. That's possible. flip ஆக்கும், upside down ஆக்கும், எல்லா வேலையும் பண்ணும் matrices. It's like a, grumbling. We say grumbling. It does all kinds of strange things. But they do these strange things. There's a way to systematically to do, create, replicate, repeatably apply. So far என்ன சொல்லிருக்கேன் நானு, rank 2 ஆயிடுச்சு, ஏதோ ஒரு matrix rank 2 matrix multiple பண்ணா எல்லாம் இந்த மாதிரி ஆயிடும். Reduce it to suppress one of the dimensions. Now think about the following. இது வரலாம் வந்தாச்சு. In other words, matrices actually transform data into a different dimensional space that could be reduced in dimension. Up to that you have come. So can we apply these kind of ideas to find out what are the most important dimension in the data? That's what the question is, fundamental question is. In principal components analysis, in principal dimensions analysis. So, you rotate பண்ணுங்க, you can suppress it, rotate it, do whatever you want. If I can bring all the things, 100 dimensions into 3 dimensions, I think that's power. But there is some cost attached to it. I told you, right? From 100 dimensions to come to 3 dimensions, there's a cost attached, because you are going to lose 97 dimensions information. Is there a method to the idea that I will somehow make sure that the 3 dimensions should contain the maximum information? I still have to lose something, but I don't want to lose, important dimensions, but I want to retain the most important dimensions and don't mind losing 95, 97 dimensions. Enama Durga, are you able to hear?
Yes, sir.
என்னாச்சு, டயர்ட் இருக்கா? சாஞ்சினி.
Yes, sir.
Straight. Yes. நல்லா நிமிர்ந்து உட்காரு. Okay. So what did I say? தூக்கம் இல்ல?
No, sir.
தீபாவளிக்குல இன்னும் பட்டாசுலாம் வாங்கல. நான் சொன்னப்பவே இதெல்லாம் எனக்கு வேணும்னு யார் கேக்குறா? அதெல்லாம் எதுவும் நினைக்க வேண்டாம். ஓகே, just let's be here, and not that you are thinking, I'm just making just for fun, because எனக்கு தோணும் வரலாம். ஏன் சார் என்கிட்ட கொடுக்குறீங்க? Alright, so switch straight. Here's the question. I made this claim. Do you agree? Do you buy this? That is, matrices transforms, rotates the space, transforms the space, reduces the space. That's a very powerful statement. இதெல்லாம் எங்க சார் நடக்குது? நீங்க சும்மா பேசிட்டே இருக்கீங்க. I want to see it is doing it. Right? You will do some problem, you'll see. But the point is, I want you to get to this conclusion. Okay? And if I can find a method where I actually grab all the most important dimensions, but lose less important dimensions, and call them as noise, that's great. Because nobody can beat me on that one, right? But of course, that method is going to be universal. Everybody can use it and use it. But that's okay. I know it now, how to do it. That's where we want to go. Get it, everybody? Where we are going. So the question is there any method that will somehow, grind it, rotate it, combine dimensions, in such a way, combine, rotate, transform the data in such a way that eventually, the rest, most of the dimensions are useless. The minimal, most important dimensions are useful, and we can capture them. That is what we are trying to do in principal component analysis, which is fundamental for dimensional reduction. We want to do that. So there is a process. For this, there is a process, concept. I said the word concept. There is a concept to do this. It's not just the transformation, but there is a more deeper, because I said this not only takes care of rotations in the space, not only takes care of compression in the space, not only takes care of the transformations in the space. All these things are taken care by one method, what is called eigenvalues and eigenvectors. Okay, eigenvalues and eigenvectors. That's what I'm going to introduce you now. அதுக்கப்புறம் தான் நான் வந்து I'm going to go to the principal component analysis. But இன்னைக்கு முடிச்சிடலாம், don't worry. It is worth spending one session. So I'm going to introduce a little bit about eigenvalues and eigenvectors. What we are saying is, இதெல்லாம் நடத்திட்டா உங்களுக்கு இன்வெர்ஸ் கண்டுபிடிக்கலாம் சொல்லியாச்சு இல்லையா? Everybody is good on that, right? Yes.
Yes.
நல்ல தைரியமா சொல்லுங்க. எக்ஸாம்ல இருக்கு ஒரு question. Find the inverse by row transformations. நல்லா தெரியல, எல்லாரும் தெரியும் நல்லா இல்லையா? நல்லா கான்ஃபிடன்ஸா சொல்லணும். Yes. You can't show this because sometimes I can't see you, especially when I'm walking through the presentation deck. You shout loudly. Am I shouting too much?
No,
sir.
No, sir.
All right. Okay. So we talked about this. How we used use the matrices to solve linear regression problem of high dimension. All those things we talked about it. Everybody with me, right? You're all good on that one. Okay. So I said I'm going to talk to you about what is meant by eigenvalues, eigenvectors. So a matrix in original space means it's a transformer of points to a new spatial relationship. How it defines new axis in the new space is the Eigen system. How it defines the transformation defines new axis in the new space is the Eigen system. நல்லா கேட்டுங்க இந்த word. Okay, I'm going to copy this. Maybe I'll copy this and post it. Okay, in the chat area. How about that? Everybody gets it? Maybe it is not too big. I mean, it is too big. Maybe 1 second. Everybody gets this point. நல்லா think பண்ணி பாருங்க. என்ன சொல்றேன்? It's very, very important point. Because you won't believe. It took a long time for me to understand this. Very long time. I am trying to make it simpler to you. So let's spend time here. That word. திருப்பியும் படிச்சு பாருங்க. என்ன சொல்றேன் நான்? புரியுதா? Everybody understand? அதுல நிறைய words நான் ஏற்கனவே explain பண்ணிட்டேன். Can somebody read and tell me every word you understand there? Please. Enna Bala?
Yes, sir. Yeah. The original space matrix, we apply some transformation and then we transform it to a totally new space. And that's why we map the function the eigenvalue vector nu solrom. அது எப்படி பண்ண போறோம் அப்படிங்கிறதுக்கு உண்டான மெத்தட் தான் இப்போ நம்ம இந்த ஸ்லைட்ல பார்த்துட்டு இருக்கோம். ஸோ AX is getting transformed to lambda x அது மாதிரி இருக்கணும் நம்மளுக்கு. இதான் நம்ம எய்ம். ஸோ அதை மேத்தமெட்டிக்கலா எடுத்துட்டு வந்து A minus lambda x காமன் எடுத்துருக்கோன்ற போது மேட்ரிக்ஸ்ல வந்து A minus lambda I is 0.
அதை சால்வ் பண்ண போறோம். அதை சால்வ் பண்ணா நமக்கு வந்து நியூ ஸ்பேஸ்ல கிடைச்சிரும். நமக்கு என்ன இது என்ன அர்த்தம்? இது அர்த்தம் என்ன? அதாவது ஏன்னு ஒரு மேட்ரிக்ஸ் கொடுத்துட்டோம். அந்த மேட்ரிக்ஸோட அந்த மேட்ரிக்ஸ் நான் யூஸ் பண்றதுனால என்ன நடக்குது இந்த நியூ ஸ்பேஸ்ல என்ன ஆகும்னா that axis might be compressed. You see, there are a lot of things are going to happen. You remember that I think a matrix skews the shears it, skews it, flips it, makes it upside down, diagonal, expands it, scales it. All these things are happening by a matrix transformation. So, if we are looking for a new space, and I want to find out what that space of what that matrix is, okay, and how it affects. That's where this is coming together. How it affects in the new space in terms of the compression, in terms of elongation, in terms of the reduction of the dimensions. All those things are determined by lambda. Let me say it again. We said a matrix transforms the data into new space. But I want to know what, in the new space, does it compress a particular axis or elongates it? Does it rotate in a certain way? I want to know that. All the things, I want a mechanism to capture those things. Those are the lambdas. Those are the lambdas, and the lambdas correspondingly gives you certain new vectors in the new space. They are called eigenvectors. These are independent dimensional vectors, and the axes are the eigenvectors are the independent dimensional vectors given the lambdas. So in one shot, the mathematics solves all these problems. And that is what eigenvalues and eigenvectors are. So, இங்க நீங்க சொன்னீங்களா அது 3 dimensional 1 1 1 எடுத்து போய் compress பண்ணி 2 dimensional மாத்திட்டு இல்லையா? So one of the eigenvalues will be 0. That's what it means. Because one dimension is gone. Eigenvalues are compressing or elongating an axis. Got it? இது compress மட்டும் இல்ல, இது நெகட்டிவாவும் எடுத்து போய் போட்டுரும். நெகட்டிவ் சைட்லயும் போலாம், compress பண்ணி 0வாவும் ஆக்கிடலாம், or it can elongate. Everybody gets this point? Kind of, just get it right now, because it takes time. You have to roll this point, rotate. Think about it many times. For an example, what I know when you're strong, I don't do it. But that's what is happening. Everybody's with me. But இது ரொம்ப நீங்க இதை பாஸ் பண்ணிட்டீங்கன்னு வச்சுங்க, நிறைய விஷயம் கிளாரிஃபை ஆகிடும் உங்களுக்கு. The factor analysis will become very clear. Correspondence analysis will become very clear. All these things are based on the eigenvalues and eigenvectors. Again, lambdas not only compress, elongates in the new axis, in the new system. Not only compress, elongates it, it can also go on the negative side. It can take a negative value too. In fact, in advanced situation, it can take in the imaginary number system also, but we are not going to go there. Statisticians don't work in imaginary space, fortunately. You work in real numbers, real situation. So, I want you to understand that yellow sentence here in this sheet. Is every word clear there? Think about it. Every word clear. It took a long time. You won't believe it. It took a long time. It's very frustrating. Of course, partly because we have other things. They think and that's it. And then I have to do the lawn mowing, or I have to go and buy the groceries, milk wine or no. It takes a long time. But the point is understanding this the importance of the very powerful concepts in matrices and how they play a role in dimensional reduction, irrespective of. It doesn't have to be only reducing into this kind of dimension, x1 to x1, y1 to 0, z to x1 to x1. Yeah, y is becoming 0. The y is compressed completely 0, right? That is not the only way. Complete or rotate pannila. Doesn't matter in whatever strange way you rotate it, and the axis doesn't have to be the same axis. It can be a linear combination of x1 and x2. All these things are in one shot. Mathematics gives the answer. That's the beauty of mathematics, and it is captured under the system called eigenvalues and eigenvectors. So if you know how to create how to calculate eigenvalues and eigen system, you are solving quite a large collection of problems. So we have to spend a little bit of time there. Unfortunately, you don't have to worry about it. You go to R and ask for that answer. It's going to give you. So it's very easy also. Don't have to worry too much worries. Go to R, you say as for eigenvalues, eigenvectors is going to give you. Okay. So calculation is not a problem. But what exactly is happening? Here is an example. You remember, so consider this example, sample example. Okay. And I said we have to create an equation like this to solve, right? This one, if I use that, this here should be here. You see this equation, this one, everybody? So I basically took the minus lambda, and then I have to find the determinant of this. This is one place determinant is useful. Okay, that's what is given, because this matrix has to be, the determinant has to be 0. If this times the x is equal to 0, this determinant has to be 0. So the determinant is cross product of this minus this. That's what it is, one, right? Cross product this minus cross product this. That's what this is. Everybody gets it?
Yes, sir.
And which is a quadratic equation? Enna Satya correctungla? Satya, Srivats. Everybody? Quite right. I didn't see you. Sometimes I have to hear you out. Everybody? Satya, good?
Yes, yes.
Now I'm seeing you. Srivats?
Yes, sir.
It's a quadratic equation. You can solve that and find an answer. Of course, I is here too, but you can do this yourself. I did it. I should to show you. This is the answer. Everybody? So I'm going to keep it in this corner here so that I keep seeing you all. Okay. So that is the answer. So what the lambda value is, lambda is, there's a formula, right? Minus b plus or minus square root of b square minus 4ac divided by 2a. Apply that. I got lambda is equal to 5.3 or 1.7. So I can substitute those values, each of these values, and solve for x1 or x2. That is the eigenvalue. For each of the eigenvalues, I can substitute and solve the equations. Everybody gets it? So I actually substituted the first value, 1.7, first value, and that becomes 0.3, right? Second value is over 5.3, right? I don't know why I have this one. No, you don't need that. So first value, okay, here is the thing. There are two values here, right? Can you rank them? 5.3 is bigger, so 1.7 is smaller. So what it says is 5.3 is the dominant direction. Okay, the next dominant direction is 1.7. Okay, everybody gets it? Because I'm going to use such words later on. More complex rotation, more complex principal component analysis. Right now, I'm just giving you as an example of eigenvalues, eigenvectors. Okay. So, 1.7 போட்டுனாக்கா 5.3 போட்டு solve பண்ணலாம், அதே போல 1.7 போட்டு solve பண்ணலாம். Okay. Those are the two eigenvectors. They are the two dimensions in the new space. Two axes. They are actually not dimensions. They are two axes. And dimensions mean, that's what I mean, axis. Everybody gets it? Was there a sound on your side? Tuck, 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 tuck? No.
No, sir.
No, sir.
I heard some sound. Whether somebody's outside. Okay. 1 second.
Answer Around 0 total 2.1.7.
15 circle.
I'm in a class right now, so
5 minus 1 3.3 3 he is considered as 2. Ada
difference போடணும். lambda 1 lambda 2 difference.
okay.
அங்க கடைசில -1 இருக்குல்ல அவங்க அந்த மேல இருக்கிறது
Don't worry about the bottom one. Don't worry about the bottom one. Just use this to solve the problem. Okay. I can find that out. What those eigenvectors are. How do I do that? Just you can solve this equation, or I can, of course, I can go to R and get those vectors. Okay. Can we do that little bit of that right now? Just get comfortable with the computational method also. All right. Either port you can take a break. Right? It's a break time. Yeah. Let's finish and then we'll take a 10 minutes break. Okay. No. Okay. I'm going to do A is here. Okay, some matrix. Are you looking at my screen?
Yes, sir.
Yes.
I think non-square matrix. Is it right? Yeah, that's why it is not. Okay, this is good example. So this matrix, how many rows and how many columns?
3 rows and 4 columns.
3 rows and 4 columns. I started working with you as an example for square matrices, isn't it? So, if I try to find eigenvalue of this matrix, I won't get it because it's not a square matrix. But there is another method for that, which I'm going to teach you, but not now. So let's define a new matrix. Can somebody tell me how do you define the new matrix? Can you say matrix? Go.
Yep.
I want to go back to this matrix, right? This one, I want to define this one. 2,
Right.
once again. This one, 2 minus 1 minus 1, 5. Can you please tell me how would I do that? 2 minus 1 minus 1, 5.
C of 2 minus 1 minus 1, 5.
C of 2, comma, minus 1 minus 1, 5. And then by
N is equal to 2. N rows, number of rows equal to 2.
By row only, yeah. Adu vendama.
By row equal to 2.
Correct. It didn't work. N rows illa. By rows no, by rows, N rows equal to 2. N row va.
in rows.
N rows N row. Okay. Now let me.
I don't think in the particular case by row தேவையில்ல. Because anyway -1, 2 -1,
Right,
3
right. N row 2 போட்டா அந்த மாதிரி வரும் அது default that's fine maybe okay but we got the matrix so just do this. I told you how to do it yourself mathematically, right? Here I told you how to do it, you just have to follow this method, and you found this lambda values and then substitute 5.3 first. No, next is 1.1, but I did the 1.7 actually. Okay, so 5.3 in this case 1.7 whatever, right? And then now you have two equations, two unknowns, solve the problem, right? Okay, but this is the computational way using this software. What do you see? Eigenvalues are same, 5.3 and 1.7. Are you with me?
Yes, sir.
And these are the eigenvectors, column wise. You have to take it column wise. But interestingly, it is, you see this one, that when I put together these eigenvectors as a matrix, it's a symmetric matrix, isn't it?
Yes, sir.
It is symmetric matrix. Interestingly, okay. Symmetric matrix. That's all I want. No, is it symmetric matrix? No, it's a negative value. No. Why do I say that? This is a negative value. This is a positive value. So I can call it a symmetric. Okay, that is a different kind of definition. I don't want to go there now. My point is, this is the eigenvector associated with this eigenvalue. This is the eigenvector associated with this eigenvalue. Now, can we do this one small experiment? Take the eigenvectors, okay? Let's do this one, square root of minus sum of, right? Square root of, that's okay, I'm going to do this, -0. Where is the, okay, 2, that means squares, right? Plus, okay, right. இதோட முடிஞ்சிட்டா இது வேணும் இதுதான் இருந்தாலும் அது இதுன்னா this goes with that. Okay, this is fine. It became 1. That's not unusual. Okay, that's what I wanted to impress on you. That's not unusual. Let's try one more time. I don't need the square root because it is 1. The square root is unnecessary. If its square root is 1, the original number should be 1, isn't it? Right? Right? Yes? No? Same thing. Everybody agrees except for some computational error, right? Rounding error. Everybody is with me? That's not unusual. That's not unusual. Every vector is what is called normed to 1. That is how in the new dimension, the new axes are determined by this. Everybody is with me? New axes are determined by this, and the distance is 1 unit in its transformed space. Okay, norm is 1. That's what we call it. Okay, so mathematically I showed you how to get eigenvectors, eigenvalues. Computationally I showed you eigenvectors and eigenvalues. Everybody with me? Do you buy that? Do you agree?
Yes.
You can do it? Yes?
Yes.
Everybody? Durga? Abhi?
Yes,
Good. Okay. Prashant? So, we have defined what is meant by eigenvalues, eigenvectors. We know how to calculate eigenvalues, eigenvectors. We know how to interpret eigenvalues and eigenvectors. We know why we need eigenvalues and eigenvectors. Yes? When
Yes.
you come back, I'm going to use this. Let me set up the problem before you go. Let me set up the problem, and then when you come back, we can explain more. So, what happens in the data, in the multidimensional data is, I want to find the way to reduce the dimension is that you see the spread of it. You understood the word? You see the spread of it. You see the spread of it. That means how they are distributed in the whole space. Everybody understand that statement?
No, sir.
Yes, yes.
No? Yes?
No, can you repeat, sir?
I am saying when you are looking at the whole space of observation, how they are distributed around the space, how they are distributed. One of the important characteristics of distribution is the location and the spread. Yes?
Yes.
Two important properties are where it's located and how it's distributed, spread out in all dimensions. Understood that what I'm talking? How do you measure that all dimensions spread? This is where, do you see this one? You do the matrix of spread instead of one variable spread. Instead of one variable variance, you are going to do the matrix of variance covariance. Got it? Yes? If I have only one variable and I want to know its characteristics, two important characteristics, location and the spread. Location is mean, spread is variance or standard deviation. Everybody agrees that. So in the multi-dimensional huge big data space, how will you represent mathematically, computationally the spread in the whole data through the variance covariance matrix? Yes? Yes or no?
Yes.
Prashant?
Yes.
Correct. Durga? Abhi?
No, sir. I'm thinking outside.
Aruna? Okay. What I said is, if I have only one variable, two important characteristics of data variable is where it is located and how it is spread. Those are the two important things for any random variable. But I have multiple variables, too many variables. How do I understand computationally the location and the spread, the total spread? Location is x bar, x1 bar, x2 bar, x3 bar, xn bar. That's a location. The mean of each of the variables. But for the total spread, how will I measure it? I'm saying it's the variance covariance matrix, which we talked about in the previous class. Are you with me? Do you understand what I'm saying? And why I have a square here, small squares here? Anybody?
Symmetric.
It is symmetric, right? The distance, the variance, covariance between x1 and x2 is same as covariance between x2 and x1. But the main point is this matrix carries all the spread. The whole spread in the multidimensional space is captured by this. Now, these are the observation space. This is the observation space. Somehow, in this observation space, there are more data in certain angles. Certain angles. There are more data points, dense data points in this multidimensional space captured by this variance covariance matrix. Agreed? There could be. If that is the way it is, in certain directions, certain angles, more dense data points are there, and in certain other direction, other angles, less dense data points are there. I don't worry about the less dense data point because it's less predictable. I want to go and capture those more dense angles, more dense axes by which I can predict better. Agreed?
Yes.
Everybody with me?
Yes, sir.
Yes.
Okay. So how do I find that more dense directions? Through dominant vector, dominant direction. How do we find that? Through the eigenvalues, eigenvectors of this matrix. Because eigenvalues, eigenvectors gives me dominance. Dominant in this case, density of the observations. I'm going to show you, graphically. But do you get that point? And basically, I got to find the eigenvalues, eigenvectors. I solve the problem. That's the principal component analysis. And I take only the top 2 or 3. That's good enough. It may not be explaining the total variance. Capture this point, word, total variance in the data. The total variance in the data is the sum of all these diagonal variances. These are variances, diagonals are variances. Do you agree? Even though I rate it as covariance x1, x1, it is variance. There is no second variance. Okay, so the total variance in this matrix, if I can explain it in one way, only one dimension in the transform space, that's fine. And I can eliminate 2 other dimensions, but that is the simplest example case, toy case. What if 100 dimensions or 200, 2000 dimensions are there, and then I compress it into 3 high value eigenvalue dimensions? I'm wonderful. I solve my problem. So basically, it is solving for eigenvalues, eigenvectors of this matrix. Variance covariance have one property. That is, variances, not covariance. Variances have one property. They are always positive. Yes, they're always positive, right? Variances are always positive. So there is, it just works out that way, that in the new dimensional space also, which are determined by the contraction, or lengthening of the axis by the lambdas, contraction and lengthening of the axis by the lambdas in the rotated new reduced space. The lengthening and contraction is really talking about how much variance is there in the new axis. Agree? The lengthening of the new axis or contraction of the new axis tells you how much variance, density, how much variance in the density of those observations in that angle. புரியுதா சொன்னது? Density புரியுது, right? 3 dimensional நினைச்சு பார்த்தீங்கன்னா புரியும். 4 dimensional 100 dimensional கூட think பண்ணலாம், அது ஒன்றும் கஷ்டம் கிடையாது. I'm saying that the whole dispersion in the data is captured by variance covariance matrix, and if I can find the eigenvalues, eigenvectors of this matrix, I have actually found the most important dimensions in this transformed space. And it's okay, as long as if I can interpret in the transformed space, I'm fine. Even if I cannot interpret, it's okay, because I can use it to model it in the reduced data space. Oftentimes that's a problem. It's a linear combination of various variables. If you combine linear combination of various variables, it may not have any interpretation, but still it is trackable. It's trackable in 2 dimensions, 3 dimensions. That's good enough. Of course, the question should be, under reduced dimensions, can we get a measure of how much variance in the total variance is explained? That's the question. In the new space, how much variance is explained from the original data? Right? That's the question. Your lambdas give you that information. That's the beauty of it. Variance explanation, each of the dimension, how much is there. The most of the variance in each of the new transformed dimension carries the density of the information. In the new dimension, how much, if it is a long axis is needed, that means most of the variance is expressed in that first dimension. So the first value tells you how much variance is. So the lambdas are indicators of the variance. Lambdas are indicators of the variance. I'm going to show you all this with example. I'm just trying to appeal to your logic, appeal to your thinking. Is that a fair thing to do? Is that a fair thing to do? Satya. Durga. கேள்வி புரிஞ்சுதா? பாலா கரெக்டா நான் சொன்னது?
Yes sir. So for 100 dimensions இருக்கு அப்படின்னா இதை யூஸ் பண்ணி ஒரு 3 or 4 5 dimensions குள்ள எடுத்துட்டு வர போறோம். ஏன்னா 100 ஆல் நம்ம பண்ண முடியாது, வெரிஃபை பண்ண முடியாது இதுல.
Time இல்ல. Most of the variance is explained here னு வச்சுங்க. Most of the variance. So why do I need it? So 90% வந்துச்சுன்னா போதும். 10%க்காக நான் 900 dimension யூஸ் பண்ண எதுக்கு? 3 dimensions are explaining 90% or even 30% is better than 900 dimension remaining 997 dimension explaining remaining 97%. Because the most of the interpretation, most of the applicability is happening in these first 3 or 4 dimensions.
And I will also get a measure of how much predictability I will be able to make with this only 3 or 4 dimensions.
Yes.
That I will be able to get the lambdas of this eigenvector.
Yes. Yes. That's what we have accomplished so far logically. So let's do some problem. How about that? So shall we do that when you come back?
Yes.
Okay. Thank you.
Sir, had called now. He said that he couldn't come today, so he requested you to upload the recorded session once the class.
So right now I'm recording right now. No concerns. So I'm going to pause.
Sir, you resume, sir?
I'm sorry. What is it?
Did you resume your recording? You asked me to.
Yes, I said that. Okay. So this is the statement. Our solution should leverage the principles of eigenvalues, eigenvectors, and our interpretation should utilize the properties of eigenvalues and eigenvectors. Very simple, right? We don't have to do anything new invention of mathematics. So let's see some example. Before I go there, Shivas, are you here? I guess.
He's coming 5 minutes.
Okay. So the PCA helps us find the most important dimensions in our data, working on the total dispersion of the data. Total dispersion of the data, it's not innocently equally distributed. Somewhere some densities happen, right? More dense data is happening and it will identify that direction for you. The maximum dense direction, the maximum dense longest direction. Okay, maximum, write down, note down that one. I want to know whether you understand this statement. The maximum longest direction which has the dense data is first identified as the first principal component, first principal dimension. Get it?
Longest direction.
First principal direction is the one that has the maximum length of the dense data. Maximum length of the dense data. Now visualize yourself. Dense ஒரு டியூப் போல வச்சு நினைச்சு பாருங்க. ஓகே, டியூப் போல இருக்கு ஒரு டைரக்ஷன்ல. அந்த டைரக்ஷன் ஃபர்ஸ்ட் ஐடென்டிஃபை பண்ணணும். மேக்ஸிமம் எவ்வளவு மேக்ஸிமம் லெங்த் இருக்கு, டென்சிட்டி இருக்கு இல்லையா, அந்த டைரக்ஷன் ஐடென்டிஃபை பண்ணணும். அதான் ஃபர்ஸ்ட் பிரின்சிபல் கம்போனன்ட். The next perpendicular to that, because your system should be each axis should be perpendicular, isn't it? Each axis should be. So next principal component will automatically find you there perpendicular to that first principal component that has the next dense longer direction of the data. So far so good. Next dense longer direction. That's what visually you have to think. Once we solve the problem, a little bit more clear. Okay, so far so far we have been talking about it. I have done all these things. Never mind. So look at this one example. Look at the screen. Do you look at the screen? This is the 3-dimensional data, but the data is located like this. Are you with me?
Yes.
Idhula vandu 3 yellow dotted lines are there. 3. Do you see that? 3. 3 dotted lines are there. One of them is orange. Do you see that?
Yes, sir.
That's perpendicular, yeah, to the pink and the red. So the better way is not that they are all same color. This is the red maximum direction. Okay, dense data is here located. Maximum direction is by red. Next maximum direction is the the way I have written it is the this pink. The way I have shown it, that may not be easy to observe because you have to look at the 2 dimension to figure out the 3 dimension. I am just telling you this is the next dimension. This is the 3rd dimension. Okay, everybody with me? But the main point is each one is a perpendicular. Again, like before, everybody understands that? Each one is perpendicular, like before. Get it? Everybody? Cool. Very cool. So, in this case, 3 dimensional போட்டுருங்க. But I can drop the lowest, dense dimension. I can drop it because it doesn't explain that much variance. So that's what we do. So the less dimension will be dropped. The less variance explained by the dimension, that dimension will be dropped, and we use only 2 or 1 something like that. Okay. So I will continue to. I just want to show you one physical, geographical example. Graphical example. The other thing is now you can also standardize the data. Why you need to standardize the data? Can somebody talk to me about it? Why standardizing the data matters? Think about it. By standardizing, what do? You make each of the variable unit independent, isn't it? By standardizing it, you are making each of the variable unit independent, and also you are moving the center to the center of the data, not to the original dimension, but to the center of the data location. So you are removing the location issues, and then you are removing the unit of measurement issue. Otherwise, income will have huge dimension spread compared to age. Agree?
Yes.
But that is artificial. We don't want that. Because we are talking about working with the dispersion, you want to work with the standardized data. Everybody understood? About Durga, Abhi,
Yes, sir.
why you want to standardize? By standardizing, you are moving the center to the data, not to the original dimension, original center 0. If I keep away all the original x's but not subtracted by x bar, I'm still in the original space. I want to go to the center of the data and then reduce make all of the dimensions independent of the unit of measurement, and then do the principal component analysis, the eigenvalue. Use the eigenvalue methods. Everybody on with me? Everybody with me or not? Yes. Say yes. Loud.
Yes,
Yes,
sir.
Apa. Nah. Make me awake. Okay. Thanks, Rivers. All right. Good. Okay, let's keep going. All right. So I'm going to take this as a case study. Application of PCA. Sometimes that the data can be skewed, right? So you want to take a logarithm of the data because it may have larger and larger values, will have larger and larger variance. So in this example, we take the log 10, okay, and then we do the principal component analysis. Very simple. This is not R. This is SAS. Okay, I don't want to use this SAS. Let's go to the R. Okay. So I want to go to the data set called. One second. I have to look into that. Where the data set is. Okay. Tool. TOURR. That package has the data set called. Let's go to the package tool first. Can you please install it on your system? So question mark tool. That double question mark. That's fine. TOURR. Okay, here it is. I have to make it big. I don't know how it's going to come. HTML file. How about I go to the HTML file? There are different data sets, but I'm going to use one particular data set called Places Almanac. Okay. I'm going to use the data set called Places Almanac. Do you see this one? Ratings of different locations across North America. Are you able to read this one? Maybe not this, but this one you are able to read, right? There are 329. Okay, so let me, so I have these two places ratings. Okay, head places. So because I attached that one, it should work. Do you see this one? And are you able to see folks talk to me? I'm not able to see your face.
Yes, sir.
Yes.
Okay. So climate, there are 329 towns, cities in USA which are rated on 14 numeric elements. 329 places, 14 elements. What are they? For the climate. They rate it so that people can, use it to make good decisions, including possibly go and live there. Okay. It's a very useful information. And its climate is rated with 521 for whatever. No, don't worry about right now those numbers, because we are going to use, in the worst case scenario, we are going to standardize it. Housing cost, healthcare, availability, usability, crime, transportation facility, education level, arts, availability of arts, recreation, availability of recreation, the economy of the place. And these are the case numbers 1, 2, 3, 4, 6. I have only printed only 6. The remaining are longitude and latitude, population size, and strata number. Okay. Oh, no, state number. I think it is state number. Okay. So we can check those variables here. Let's see whether I can get it here. I don't know. So that's where this can help. Perhaps. Wait. Places Almanac. Okay, that's what I'm going to analyze, show the analysis of. So why? Okay, let me go and do a little bit of research. Places Almanac tool package. I need to write it down. It's already there as tool package. Okay, that's fine. It is here. I want to description of variables in Almanac. Okay, let's see here.
It's two.
1 moment.
Library.
You should download and install TOURR. Okay, in the meantime. Everybody with me?
Yes, sir.
Okay, I'm trying to get the definitions for the variables. 1 moment. This is what I already have it. It's okay. That is fine, but education, okay. Stay. I think that's good enough. I think we don't need anything new. These are the variables, okay? Climate or terrain, housing, how favorable these are all, okay, in general. 329 communities. So I want to note it down here, keep it there so that come back. Search again.
In next library of
say this. Oh, what I want to go here. Somewhere I meant R code was there. Okay, so the idea here is that I need to let me get you, some other reference. Let me see whether I have the reference here. Somewhere I lost it. I don't know. Okay. Why? Okay. I don't know why I lost it. Ourselves, no problem. Okay, so what happens is that we want to drop these things. We don't want these things. Do you all agree with me? Case number, we don't want longitude, latitude, population. Maybe population we can keep it, but state number, these things we don't need it. Okay, everybody? Actually, I want 1, 2, 3, 4, 5, 6, 7, 8, 9. First 8 variables only, 9 variables only we are going to use. The remaining we don't need it. Do you understand why I am saying that? Everybody, do you understand why I'm saying that? First 9 variables only we are going to use for the analysis, okay? And I'm going to replicate this analysis done in SAS. We are going to replicate it in R. Okay. Now, what I want to do is, first, I want to do the, because that SAS case study used logarithmic transformation of the variable, I'm going to do that one. So I have here what is called the places, right? Places is the one, the data set we are talking about, places. Okay. I'm going to make a log P is equal to, I already have log 1P. Log P is equal to logarithm to the base 10 of places. This will be valid only if places doesn't have 0 values. Everybody agrees with me? Everybody agrees with me what I said? That transmission I can do only if the values in the places are none of them is 0. Everybody agrees with me? Yes? I can't do transmission of 0, log transmission of 0. That's the reason. Everybody?
Yes, sir.
Minus infinity.
Yeah, but anyway, it should work out. Otherwise, it's going to complain for me. So I'm going to work it out as if everything is cool. Let's see what happens. If it works out, everything is cool. That means no 0 values. Oh, I have to drop everything I said, right? So let me do. I'm sorry for that. I cannot use some of the things I told you, right? So what are they? I cannot use minus C of column. No, I want to use only columns 1 to 8. Is that okay? 1 to 9. Is that okay? That's what I want to use. Oh, I didn't. Very simple. I took logarithm base 10 and I also removed the 10, 11, 12, 13. 10, 11, 12, 13. Okay? So you can see what log P looks like. Everybody understand what is meant by log P?
Yes.
With respect to base 10. Why do I do that? It's because, in the case study, that particular case study they used, and they used it because the larger values have larger variance. Are you with me? The larger variables have larger variance. Okay, so I use this one now. I can use this to find my principal directions. I just have to do the Eigen, isn't it? If that's all they did, I should get the same answer. But there are packages that actually does all these things for you. Okay, why don't I do that? No, I'll come back to that. Wait, it's not a square matrix. Oh, same problem. Okay, it's not a square matrix. So there is a way to handle all those things, and I don't want to confuse you, but we have gotten into this ourselves. Myself, I have to explain it correctly to you. Okay, so I'm going to do something else. So I just have to use a command, what is called prcomp. Okay, prcomp x scale is equal to false. In this case, I'm going to start with scale equal to false. Okay, prcomp. So let me store the output as PR. There is nothing there. PR is prcomp of the log P. Scale equal to false. What are the members of PR? So I'm going to list what are the members of PR. I have this center, rotation, scale, standard deviation, X. Okay, I want to know what they are now. The problem is pretty much solved here, but I want to interpret it for you. In order to do some graphics, I also need another package. In order to do graphics, I also need another package, Facto Extra. I'm going to do that. Okay. Install package Facto Extra. I think I have it already. Facto Extra. So I'm going to install that one. Library Facto Extra. There are some graphics I can do, so that's why I'm loading that also.
The package name another. The package, எந்த package install பண்றீங்க? Name of the package what you are installing?
Facto extra. Facto, I will type it, huh? One moment. Install package, this one. The latest version is available in GitHub, so I went to the latest version. You can just do this. Okay, why don't you also do the same thing? Use the latest version, because otherwise there is possibility that we may get different results or different output types. So did you get that message? I have given the command here. Did you see that the package what I installed? See, this is a problem now. If you install, sometimes it creates a lot of work. I don't know. Maybe I shouldn't have done. Anyway, it's done. Okay, factor extra is done. I'm going to go to the library and call it as library. Library. Factor extra is not coming. I don't know why. So maybe I have to refresh there. I don't know. Okay. So factor extra is also with me now. Okay. It will help me to do some graphics. I'm hoping that the graphics is fascinating for you and you like it. Now, places, right? I want to do. I don't know whether they have places almanac. Okay. So you didn't use the places almanac. I'll do 2 of these case studies. So let's do this one. Print comp, PR comp, we said that, right? So just park the idea of factor extra for now. PR comp has these, I went back there, right? PR. I have centered, rotation, scale, standard deviation, and the X values. Okay. Now, to the PR comp. So remember that it doesn't have any response variable, right? We just gave the data, nothing else we did. Okay, standard deviation refers to standard deviations of the principal component. So let's just print that one. SDEV. So these are the standard deviations of the new variable. The new variables are in this transformed space. Okay. Do you see that it is decreasing order? Everybody sees that it's a decreasing order, right? So if I want to select only 2 dimensions, which are the first 2 and which are the 2 dimensions I will select? The first 2, because that is supposed to be representing the maximum variance if I have to use only the first 2 dimensions. If I use the 3 dimension, these are the 3 dimensions I have to consider, okay? Which refers to, in this case, first 3 dimensions, which refers to these first 3 standard deviations. So in the new dimension space, first dimension principal component has this variance, not this variance, this is the standard deviation. Second principal component has a standard deviation 0.2259. Third dimension has a standard deviation 0.167. And if I use this one, the total variance is total, if I want to use the variances, it is really PR. If I want to calculate variance, it is just the PR as def square. Everybody agrees with me? This is the total variance in the data. Everybody, do you understand what I'm talking? I explained this before. I'm calculating here. Where am I going with this? So far, so good? Where am I going with this? There's a very important step we always do. We want to know, let's say I select first 2 dimension only. I want to know how much variance in the total variance is explained by the first 2 dimension. Is this a common problem we do, right? How much variance is explained? Everybody?
Yes, sir.
So if I want to calculate how much variance is explained by the first two variances, how will I do that? Anybody has an idea? The total variance is this. I want to know first two variances, how much it explains. So how will I do that? It's a simple mathematics.
Just add those two variances, sum of these all variances, divide it.
Everybody understood what he said? You add those two variances, 0.377 plus 0.051 divided by sum of all these variances. Get it? That tells you how much variance is explained by the first two dimension. And Durga, correct me?
Yes, sir.
Durga and B. Satya. So first let's find out what is the total variance. Total variance is basically sum of this PR dollar, dollar SDEV square, right? Just sum them, which is 0.52. So out of that first two dimension is, I can do this, right? I think I can do this. 1, 2, 2 divided by. Can I do this? Will it work? Which? Let's just say first this one, 1 to 2, whether it's coming through. Yes, it does. No, 1 to 2. Why is that? It gave me only, oh, sum. I did the sum, but it gave me all the things. Okay, fine. I want, I'll do this. PR, let me just do this PR square, okay? PR square equal to, no, PR standard, PR var, okay? That is the variances, PR dollar SDEV square. And then I can select easily, okay? Now, PR var 1 means first one, agreed? PR 1 to 2 means 1 and 2. Now it works, okay? Everybody? So what do we do? Sum of PR var 1 to 2 divided by sum of PR var. Everybody agrees? What does it say? Can somebody tell me? We actually interpreted this.
Yeah. 82% of the variance can be explained by only these two parameters out of the 8 or 9 parameters we have listed.
Not parameters, two principal axes. Stay that way. The first two principal axes explains 82% of the total variance in the 9-dimensional space. Everybody gets it? Isn't it cool? You solve the problem. These two dimensions are powerful, isn't it? Let us go to the bottom two. We'll see what happens. How about that? Shall we go to the bottom two? See what percentage it explains. Obviously, it's going to be small, isn't it? 1, 2, 3, 4, 5, 8 and 9. Okay, 8:9. How much it does? Bottom two, 1%, isn't it? How about bottom 5? 6, 7, 8, 9. 5, 6, 7, 8, 9, including 5. Okay.
3, 4 quota 0.09.
3, 4 quota 0.9. That's what, right?
3, 4 3 and 4th variance substitute 0.09.
Yeah, that is fine. I don't want really to. I'm laboring too much here to continue to spend time there. We don't need to. My main point is that all these dimensions are ranked. All the importance of these dimensions are ranked by the eigenvalues for you. And the eigenvalues are the variances. Okay. So, interesting thing is, you remember it said you cannot solve the problem because it is not square matrix. But interestingly, you can solve the problem using A prime A. That will become a square matrix. But anyway, I don't want to go there. For right now, let's solve this problem. That it is solved. I know what are the dimensions. So now I need to know what are the dimensions, right? I have to explain the dimension. First eigenvalue, eigenvectors. First two eigenvectors and first two eigenvalues explains 82% of the variance in the whole 8-dimensional space. Get it? Some people ask you in the interview, explain to me, what is meant this 0.82? Everybody gets it? Yes, you can show like this. You don't want to talk.
Okay. Again.
Can somebody introvert? Bala, you said something. Can you repeat that? First two.
Yes, for first two, we have identified some access parameters. So out of which we are going to find which are
parameters. Two new dimensions.
Which
is an axis defined from the previous dimensions.
So two new dimensions we are going to find out by this analysis, and we are finding out the variances of the individual top 9 variances we have found out, and out of which we are trying to see which are the combination of which of these gives the most number of variances explained in the model. So in that we have found that the first two itself are able to explain 82% of the variances, whereas the last.
Yeah, good. Let me restate what you were saying, okay, Prashant. So, first of all, you understood how to get the solution, principal components, directions. The principal direction, I'm going to show that to you. What vectors define those directions? Vectors are defining a direction, but right now, how much variance is explained by each of the direction is what I'm telling you. Okay. Those are explained by the, there is a relationship between the standard deviation and the eigenvalues. I don't want to go there. It's already printed for you. I use the package called PRComp. There are different packages. You can use PRComp. That's fine. With PRComp, I have solved the problem basically. Okay. After I took the log transformation. Log transformation I took because the case study that is used SAS used log transformation. Okay. We use these transformations to be more meaningful. Sometimes we do the standardized variable also. In this case, it's not used. Okay, whether it is right or wrong, that's the next question. But in this case, it's not used. We want to use standardized. Okay. So when I saw the problem, I got the SDEV. That is means these are the standard deviations of the new dimensions. And these standard deviation, I can multiply it into, I can make it into variance. When I square it, it becomes variance, each one of these. And when I sum the variances, it comes to 0.5223 in the log space, logarithm space. Remember that 0.5223 and so on. These are total variance in the data. But I want to, in the new space, I don't want to use all the variables. I want to use only the top ones. I want to use only the top two. 2 or 3 people use that, say most of the time. Okay. Interestingly, it so happens with top 2, I am able to explain 82% of total variance. That's all I'm saying. Isn't it cool? I think it is cool. Okay. The powerful mathematical method helped me to not only see the direction, which I still haven't shared with you. The directions are coming from the eigenvectors. Vectors are always about direction. You remember, everybody? Vectors are about direction. I haven't talked about it. I'm still worrying about only the lambda values, the standard deviations or the variances, because I want to know whether it's a worthy exercise. I say it's worthy exercise because with 2 dimensions in the new space, which are called the principal components. These 2 are called principal components. They are the most important axis, and they explain the density of observations in what direction, maximum density and variances, and that turned out to be 82%. Everybody's with me? Everybody?
Yes, sir.
Satya, excellent. Srivats. Now we want to know which direction. Directions are given by vectors. In this case, eigenvectors. The new eigenvectors. The original eigenvectors na enna solluva? Original data of enna eigenvectors? Can somebody tell me? If we tell that, that's you get a star. In the original data space, what are the eigenvectors? No transformation happened. So what are the eigenvectors? Identity vectors are the eigenvectors. Everybody agrees? Correct? Durga?
Yes, sir.
Okay. And Abhi?
Yes, sir.
So original வந்து அதேதான் 100 010 001. Those are the eigenvectors there. But we don't want that. Why? Because it is representing 8 dimension and 9 dimension. I don't want that. I want in a new space. But the new space is going to rotate the data in a way that it captures the maximum variance in fewer dimensions. But when it rotates the data, the axis, the axes are changed. The axes are determined by the eigenvectors. And so we are going to see what those eigenvectors are. That is very simple. That's what the x, I think it's also x-axis, right? So let me see. PR dollar x. You see, oh, this x is the data. X is the data, okay? Because it is going beyond 100 and beyond 100. We don't want that beyond 100. Because the remaining is x is the, in this case x is the data. Okay, so we want to find out. Let me see, how is it coming along? You know what? I can do this. Okay. Oh, okay. For some reason, loadings fit, plot fit, lines fit. So okay, they are called rotation in this case. Okay, different packages have different ways of writing it out for you. So PC, so PR dollar rotation 1. Let's see what happens. PC dollar rotation. Okay. Do you see this one? PC dollar rotation. I mean, PR dollar rotation. PR is the one that has the object, right? Output objects, and that one, the rotation is the one that is giving you the principal vectors. Is everybody with me? Yes, very straightforward. Just call PR rotate the rotation object that is giving you the new vectors, the directions. The new vectors are defining all the points in the data space. Everybody understands? The 100, 010, 001 in the original space in a three-dimensional world. The original space is 100, 010, 001, right? They are the eigenvector. They define the whole space. Every observation is defined by that. But you need a new vector, which is what these things are. It's very complicated because it is rotated. The whole space is rotated in 9 dimension. Am I making sense to you? So the first principal direction is this one. Everybody gets it? The first principal direction, if you remember, direction is vector. The variance is lambdas. Okay, so first principal direction is this one. Everybody gets it? What is this one means? PC1. Everybody gets it? I've been consistently saying that, right? Everybody. Enapa, Prashant, correct? Durga, Abhi, what about Aruna? கரெக்டுங்களா?
நமக்கு 9 வேல்யூஸ் இருக்கிறது, அந்த 9 வேரியபிள்ஸ் தானே 9 வேல்யூஸ் காட்டுது. அதுதானே நமக்கு அந்த 9 ஐகன் வேல்யூஸ் வந்தது.
It is saying basically you have to weight climate data by this factor. In the matter of linear combination like these variables, you are linearizing and getting combination of those with these ways. That is your first direction.
இல்ல நான் என்ன நினைச்சேன்னா, இப்ப 9 வேரியபிள்ஸ் இருக்கு நமக்கு. கிளைமேட், ஹவுசிங் காஸ்ட், ஹெல்த் கேர், கிரைம், அந்த மாதிரி 9 இருக்கு. இந்த 9ல நமக்கு 2 தான் சிக்னிபிகன்ட், ஏதாவது 2 தான் எடுப்போம், மிச்சம் 7 டிராப் பண்ணிடுவோம். அப்படிதான் நான் புரிஞ்சுக்கிறேன்.
பட்
நமக்கு 9மே லிஸ்ட் ஆகுற மாதிரி தானே வருது ஒரு வெக்டார்ல. இப்ப நம்ம பாக்குறோம்.
இல்ல, you have to, what are you doing? You are transforming the original 9-dimensional space into a first 2 or 3 dimensions. So that means these vectors are not useful. That's what we are saying. It is a linear combination of the original data. So this vector and this vector defines 82%. Vector is the direction. You need direction and the spread to explain. Ipo puriyudha? Kind of. What she asked is a very important question. Everybody will have this kind of confusion. 2 dimensions. First of all, numbers. I'm still keeping this data up in run. I'm saying, in order to know this transformation in the new space, you still have to use the old data. You are transforming the data into a new space. And the new space has these 9 directions. These 9 directions refers to the new space. But the thing is, the first directions alone explains 82% of the variance in the whole data. But these are all linear combinations of the original data. You are not jumping suddenly anywhere. It still has to be related to the previous dimension, previous data, previous variables. So these are the PC1. It refers to the vector directions of each of the variables. If you do this transformation for all your points coming from these climate, housing data, all those things, then it will take you to the maximum variance direction of the whole 8-dimensional space. Prashant?
Yes, sir.
Durga? Abhi?
Yes, sir.
Satya? Bala?
So இதுல for example PC1ல இருக்கிற ஒரே ஒரு காலம் மாத்திரம் நம்ம எடுத்துக்கிட்டோம்னா, அதை எடுத்துட்டு போயிட்டு ஒரிஜினல் ஸ்பேஸ்ல இருக்கக்கூடிய அந்த 9ஆல ஃபர்ஸ்ட் ப்ரீ மல்டிப்ளை நாம் பண்ணோம்னா I will get a new space அந்த டைமென்ஷன் இல்லையா?
And it will capture the maximum variance in the spread in the data. So இப்போ வந்து இது ஒரு maximum variance இருக்குது, இப்படி கொஞ்சம் variance இருக்கு இந்த direction வச்சுங்க. Okay? And in third direction கொஞ்சம் இருக்குன்னு வச்சுங்க. This will be captured all the points in the new space are the transformed values of the values given here. For any vector you get from the old, you try weighted by this. You get the new point in that new space. And every point should have a point there, right?
Okay.
But this time you are only using 2 dimensions. The remaining dimensions, they're all there, but they're all compressed. Remember that one of the y is compressed. That turned out to be second dimension, third dimension, 4th, 5th, 6th, 7th, 8th, 9th. All those things are compressed to 0. Think about it. Everybody with me?
Yes, sir.
Excellent. So now, you got the principal components, you got the variance, how much variance is it?
Pudusa data. Adu maximum variance combination.
Maximum variance
Now,
data.
PC1 maximum variance data model. So all of them 82%.
Original data
I'm going to do some plots for you, okay?
One by data.
So let's do the another data set, okay? And in this case I have some graphics I can show you. What is called USARS, okay? I mean USRS, that different crime categories, USRS. So that data is available here. Okay, I want to share with you this data set and do this analysis, one more analysis. Are you looking at this one? Everybody? That is, Alabama has the arrest rate of 13.2. I think it's for 100,000. Okay, yeah, let me check it. So, number of murder arrests, Alabama has 13.2, Alaska has 10. Okay, just top 5 alone, 6 alone. Assault is this much, urban population is this much, rape is this much. Okay. Is everybody listening to me? Is everybody listening to me? At this one. There are different crimes by state. Okay, USRS is available in our studio. Okay, automatically it will come. Okay. Now right now it is okay. So on a small data set, 4 dimension, but can we still explain it in 2? Okay, 2 dimension. That's a very natural thing because 2 dimension is easy to understand. Even 3 dimension is difficult to understand, even though 3 dimension is visually possible. Now, so let us do that PRCom. I'm going to use only PRCom today. Okay, now, there are many ways to do it. I'm going to use PRCom. So I just run PRCom, PCA, apply PCA. Okay, let's do this because I can show some interesting graphics. That is the idea. So let's do this one. I don't want to use any graphs at this time. PRCom. Extra argument graph will be disregarded, that's fine. So I want to see what the objects are there. Center rotation scale as given. Okay. But what I want to do is I want to print it and show it to you just 2 dimensions. Before I go, I want to see the standard deviation. PCA 3. No. PCA 3. Okay. So first 2 dimension alone. First 2 dimension alone, how much it is? So we want to go to the variables. Sorry about that. I want to check it out. Okay, I keep hearing this voice. I don't know why, and that must be difficult for you. Okay, the point is, yeah, you keep. Are you able to hear me well?
Yes, sir.
Yes, sir.
So 99% variance is explained by 2 dimensions. Isn't it cool? So there is a, what does this mean? Really, there is a linear relationship among those variables. That's what it simply means. So you don't need other variables to continue to be in the data set for you to handle, to explain, and to predict. Okay, so 2 variables is but those 2 variables are in the transformed data space. Those 2 variables are in the transformed data space. Okay. Now I want to show you, I want to conclude this with a graph. That's why I'm going, that's why I'm going, because it's easy to do. For that, for some reason, data put scores. Let's see whether this works. Okay. Okay. ggplot data is equal to scores. Instead of scores, I have to put x because x is this. Scores is same as PCA 1x. Yeah, it is a vector. It's a vector. Scores and then AES x equal to PC1. X equal to y is equal to PC. What did we get? PC1, PC2. Rotation PC1, PC2. PR. Let me do this before. PCA3 $ X $. The dollar is done. PCA3 X 4. This now axis matrix. Axis matrix. I want this to come out. No, I'm taking a wrong one. That's the reason why I didn't get it. Okay. Operation values. Okay, yeah. See, I was looking at this one. This is right. Okay, the first PC1 is this one. Everybody? The second PC1 is this one. Okay? Everybody? So now I want to, yes, instead of scores, data is X. X is the original data. Let me see one more time. Data is rotation. I'm taking a risk by doing something new here. Rotation, PC. Just don't write anything, okay? I'm rotation. Scores. I'm interpreting in my way. PCA1, PCA. Okay, let me do one thing. I want to do it differently. Okay, it's better to do that way. PC. I'm using PC1. No, did I scores? Method is it's the first method. Here is the first method. Okay, PR comp. That's right one. PC1 is right one. So I just have to name it correctly. I'm going to use this PC1 or PC3. I think everything will fall into place. PCA1 is equal to PR comp. CRS scale Okay, I just changed it from PCA3 to PCA1 just to make sure that there are no errors in the code. Okay, so again, I'm going to go back and show you that the standard deviations are this, which is same as before, but just showing it to you. Okay. All right. Next one is the rotation. Okay, rotation refers to the vector. Okay, the direction. So the whole rotation here you get the PC1, PC2, PC3, PC4, and so these are the direction of the new in the new space. These vectors define the direction. In the old space, it will be 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. That was the original space. That was the eigenvectors. Which is the unit vectors. In the new space, these are the vectors. The vectors refer to the vectors. Okay, so we got that. Now I can also calculate the scores. These are the scores. These are the scores. Okay. Let me tell you what the score means for you. This is a new word that we have to know. Scores are logical. The coordinates of the individuals on the principal components. Okay. So these are the calculated values in the new space. Are you with me? These are the weights of the axis, but these are the calculated values in the new space. Everybody with me? That's what scores means. Okay? You can write it down if you want. I think you need it. You need to keep that one. So
sorry, sir. are these the weights that I have to apply on the old dimension to get into a new space, or are these itself the new values?
These are the weights you use to get into the new space.
Okay, so I have to multiply this with the old dimension values to get a new space. Is that right?
Yeah.
Okay, thank you.
So let me go back to the finally I want to come to this, the graphics. That's what the most important. See, there are many methods to do it, but I know we don't want to go back to many methods, but the important thing is create data from data frame with scores as data frame so that I can print it, and that will be used to plot using ggplot. Okay. Why it didn't come through? What happened to the plot? ggplot. Why did it come through? I'm supposed to speak. And oh, a viewer. Plot. Thank you. All right. Now, this is the new axis in the new space, PC1, PC2. I have only two axes I'm using. Okay. Everybody are able to see this one? Everybody, you are able to see this one, right? Okay. If you look at this, just two axes I'm using to explain the variation in the four types of errors. And this is good enough to explain 4 types of errors. 2 dimension is enough to explain 4 types of errors. If you look at these things, West Virginia, Vermont, these are all rural areas. Do you see? I don't know. You may not know that, but I know. Okay. These are all rural areas. North Dakota, South Dakota, West Virginia, Vermont, Kentucky, Montana. These are all rural areas. If you look at this one, these are all I'm coming. This is rural area. So if you look at this one, this is kind of a little bit more urban area, right? Pennsylvania, Connecticut, Massachusetts, Hawaii, New Hampshire. New Hampshire is in the middle. Okay, so don't worry about it. So if you look at this one in this direction, these are all urban areas. Okay, Washington. Okay, everybody. And then this is rural, this is urban, this is what. So I explained this direction now. This direction I'm going to go. If you look at this one, Georgia, Louisiana, Alabama, Tennessee. Oh, by the way, crime rates. Okay, that's fine. But Georgia, Alabama, Tennessee, South Carolina. These are southeast. Alabama.
More of,
I'm sorry?
More of rural, less of urban?
Here you mean more of rural, less of urban. Okay, first let's see the, let's see what PC1 refers to. Okay, PC1 refers to, I need to interpret that for you. Okay, PC1 refers to, all of them are less, weighted. All of them are weighted less. You see this one? Negative, 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 negative. Okay, where that is this one, PC1 refers to in this direction. Are you with me? PC1 refers to this direction. PC2 refers, because I know this PC1, it says that PC1, right? X-axis is PC1, Y-axis is PC2. Listen very carefully, because this is what matters here. PC1 refers to reduced crime in general. All crimes are reduced. Okay. On the other hand, PC2 refers to a lot of murder and assault, but extremely less urban population and rape. You see this one? That is why this way, okay, these things come out to be like that versus this way. If I compare this way, you see, you talk about murder more here, assault more, but less urban population and less rape. Sorry about this graphic murder cases and so on. Just cool your anxiety. Just interpret it here. Okay. What I'm saying is this way you are talking about all of the crimes are on. I'm talking about this axis. Okay. But if you compare this way, you are comparing more of murder. Here more murder. Here less murder. Here more. Less urban population and less rape, and here less murder and less assault, but more urban population and more rape. Am I making sense to you? Think about it. So these states are classified in that sense. So accordingly, what we are saying is, PC1 is this way, it goes like this, right? This is the x-axis, the PC1. On one hand, Florida, on the one extreme, the other extreme is New Hampshire, Iowa. And New Mexico is included here, New Mexico, Michigan is included here. And so this is New Hampshire and Iowa. What I'm saying is, this is PC1, that is the first axis, which is weighted like this here. Extremely less, in this case, extremely less. When it is positive, extremely less. That means when it's negative, it's extremely more. Are you with me? So one way to understand is go back to the original data and see whether it makes sense. That's another way, right? Not this one. What is the original data? Data of USARS. So what about let's take the Florida. Florida is murder is extremely more. Are you with me? Are you with me, guys? That's exactly what is captured here. On the other hand, New Hampshire, let's go to the New Hampshire. New Hampshire is, you see this one? Extremely low compared to Florida. So it comes out to be the opposite here, because New Hampshire is here, Florida is here. Is everybody with me? Kind of. Just comparing the original data and how the PCAs have captured that into 2 dimensions. Not only that, it also captures other things too. Weighted by those weights, right? Those weights are given by PC1, PC2. Only 2 vectors are weighing them, projecting them into 2-dimensional space. Projecting them into 2-dimensional space, because I took only 2 dimensions. Is that clear?
PC1 by itself is not one single parameter. It is a combination of 4 parameters by those weightages. And similarly, PC2 is not one y-axis. It is a combination of, again, those 4 by those weightages.
No, they are only one. They are pointing out to an axis. If you remember, a vector is a direction. You have to remember this. It's in science, physics, you have learned perhaps, those who did the physics, vector means a direction. So the 4 dimension is directing to a point in 4-dimensional space. But the thing is now, only you can project all these things into 2 dimensions, because it only matters only 2 dimensions. 3 and 4 doesn't matter. Okay. So answer to your question is, repeat the question. It's not 2 dimensions. It is projected onto a 2 dimension in a 4-dimensional space.
Yeah. So my statement was PC1 by itself is not one single parameter or one single direction. The direction means it is a combination of 4 parameters given by those weightages.
Yes. In original data, it is again same thing, but it's a unit vector.
Right. But they will have, correct. But 4 of them will be 4 different units based on those 4 unit vectors.
Original units. In the original units, 1, 0, 0, 0. That was your original weighing vector. But now your weighting vector is different. That is what PC1, PC2 is. PC3, PC4 is. So 1, PC3, PC4. PC1, PC2 is good enough. Each of them tells you the direction. On that direction, maximum variances are spread. Those 2 directions. Is everybody with me? Okay. Rest of you. Lot of little thinking you are, put yourself into this. Take this, think about it, come back tomorrow. We'll redo this again and do more.
Sure, sir. Sure.
Everybody? I want to finish also factor analysis tomorrow. It's possible. They same thing, but in the hidden dimension of we are going to work.
Oh, okay.
With that, I will stop here. Is that okay, everybody?
Sure, sir.
Sir,
Yes, I'm finishing up. Give me a few minutes. I'll call you back. 2 minutes, 3 minutes. Okay. Yeah, ask me the question now.
So PC1 ஓட values இருக்குல்ல அதுல 4 values இருந்ததுல்ல நம்ம அந்த வெக்டர்ல அந்த பாசிட்டிவ் நெகட்டிவ் இன்டர்பிரேட் பண்றது மட்டும் ஒரு தடவை ரிப்பீட் பண்ணுங்க. இப்போ இந்த ஃப்ளோரிடா நியூ ஹாம்ப்ஷயர் வச்சு
புரிஞ்சுதா? அது ஃப்ளோரிடா நியூ ஹாம்ப்ஷயர் ஏன் அவங்க ஆப்போசிட் டைரக்ஷன்ல இருக்குது இல்லையா? ஒரிஜினல் டேட்டா பார்த்தது நல்லா கிளியரா தெரியுது.
பார்க்கும்போது புரியுது. இது கொஞ்சம் அந்த PC1 ஓட ரிலேட் பண்ணினா இன்னும் கொஞ்சம் பெட்டரா இருக்கும்.
Okay, of course. PC1 ல என்ன சொல்றது? It says murder is assault, population, urban population, rape, everything is less.
Okay.
Compared to the middle point. On the other hand, PC2 says murder and assault is more than the center point, middle point. But they have less urban population rape. So if I find urban, PC2 should help me to differentiate this intelligence to differentiate. They should have more murder and assault, less urban population rate. So that is this direction. Okay.
இப்ப ஃப்ளோரிடால வந்து நம்ம மர்டர் கம்மி அப்படினு சொல்றோமா?
PC1 is this direction, PC1 is this direction, right? Murder நம்ம சொல்லல. நம்ம ஏன் சொல்லலன்னா it is going on the negative direction. So it is a negative of negative, right? See, this direction is less murder, less this way. This direction is less murder and less assault, less urban population, less rape. But here this direction is actually more murder, more assault, more urban population, and more rape. So Michigan, more urban, Texas, more urban population. This is somewhat an anomaly. I don't know why it is coming, but sometimes you may get overall, it's all about overall, right? Sometimes it might be an issue, but it is below this one here, right? So we are talking about this direction, PC2. PC2 direction is here, it should be less murder, less assault in Nevada compared to Alaska, okay? Because I'm trying to put the same thing here. Let's say Alaska and Arizona. Compare Alaska and Arizona. Here it will be less because in the negative direction of PC2, right? The negative direction of PC2 means I will have, less of the murder, less of assault, more of the urban population in this current direction. Okay, so compared to Alaska, Arizona is true. New York is true. New York and Arizona is very close, right? Illinois, Colorado, Texas, these are a little bit more urbanized compared to Alaska and Georgia, Louisiana, Alabama. So go back and think about it. Let's revisit this again tomorrow. Okay?
Sir, can you send the recorded session?
Yes, I will put it, yeah. I got to leave now, so I will, by the time it will get translated into MP4, I will put it today evening or afternoon. Okay, thanks. Everybody good? Just hang in there. You have got some wealth of information here. You have to just package it correctly. Thank you. Bye, everyone.
Thank you. Bye. Bye, sir. -0.3